Okay, in this video, I want to introduce square roots. And before I introduce square roots, I must introduce this idea of the area of a square because it turns out that the area of a square and square roots are very closely related. And I want to introduce the area of a square because I don't want to assume anyone watching this video at this point knows how to find the area of a square, what that even means. So let's talk about that first. Let's say I have a square, and let's say that in this square, or for this square, this distance right here for this bottom length of this square, let's say it's 2. And let's say that this length right here has a value of 2. And here's one of the constraints, or part of the definition of a square, is that if a shape is a square, every single side must have the same length. So if I'm saying this is a square, the only way it could be a square is if not only these two sides had a length of 2, but also the other two sides. And so that would satisfy one condition of being a square. There's one other condition for something to be a square, is that the angles between all the vertices, or the points where the lines meet, the side lengths meet, they all have to be 90-degree angles. So every single one of these angles has to be 90 degrees. If it's not like that, if you don't have all 90-degree angles, and if you don't have the same length for every single side, it's not a square, it's something else. So anyways, I'm telling you this is a square, and I'm telling you that, I know it's not perfectly drawn, but assume, based on what I'm telling you, that every single side has the same value. It's 2. Now, another thing I want to talk about is, let's specify a couple things. Because usually when we talk about area, we talk about this idea of a length and a width. And this is when we're talking about the area of shapes like squares and rectangles. So we're not talking about rectangles right now. We're just going to talk about squares. So if I call this side, it has some value, some length value, and I'm saying it's 2. And normally we would call the other one width, right? This dimension here, right? So when I say dimension, I mean the direction of the distance that we're talking about. So we're talking about a direction going this way. I know it's kind of crooked, but that's somewhat good enough. So that would be like one dimension. The other dimension would be going this way. And notice that I only need to specify these two different dimensions, length and width, because notice this top side of the square, well, that's going in the same direction as this length. It's the same thing. And similarly, we have, this would also be width. I don't need to specify it. I've already specified it here. So I have two dimensions, length and width, and squares are two-dimensional shapes. They don't have a third dimension of height, which is something you would see in the real world, right? You'd see something that has maybe a length, a width, and a height. If you're talking about, I don't know, like a box, maybe a book, right? The height could refer to some thickness of that object, right? But I'm not talking about that. I'm talking about a two-dimensional square for now. And I want to talk about the area of that square. Area, when I say area, what I mean is, I mean that the amount of space that fits inside the closed boundary of my shape. And so when we talk about two-dimensional, shapes, we often talk about the area, the space that fits within the boundaries of that shape. One close example in the real world of like a two-dimensional shape with area, but it's not quite, because everything in the real world technically has a height. You could think of like a sticky note. Usually yellow sticky notes, right? They're usually, not all of them, but some of them are shaped, like a square. All the lengths are the same. And then they are so thin, you could think of it as having almost no thickness, although technically it does, right? Very small thickness. But I want you to imagine something like a sticky note, but with no thickness. It's literally flat as flat can be. And the only area, when I'm talking about, the only space I'm talking about is just the space that is inside the boundaries of that shape. Okay, so how do we even begin to discuss or quantify how much area or how much space is confined within. I mean, there's, depending on how creative you want to get, there's an infinite number of ways. You can say, you can calculate area by the amount of jelly beans that you could fit within the boundaries of this, or the amount of checkers or whatever. But that isn't that useful, right? Because those would not fill in all of the space, right? If it was a bunch of checkers, you'd have a bunch of circles sort of butted up against each other, and like, hey, what about all the space in between them, right? If you had like 4 checkers in here, I know I'm not really drawing them butted up, but you have like space missing. So that technically could be a way of quantifying, the amount of area in it, but you could say like, oh, I could fit 4 checkers in here or something. But we have a better way, actually, a more mathematically rigorous way of doing that. And what we do is we try to say, okay, what if we had other squares that were of length 1? So smaller squares where every single, that's a terrible square, I apologize, but imagine if that length right here was 1 and this was 1 and everything was 1, and we want to take smaller squares with length of 1 everywhere. We want to see how many of them can we fit inside our bigger squares, right? And so how can we go about figuring out how many one by one squares, right? When I say 1 by 1, I mean length, right, by width. So the length technically is 1, and then the width is the same. It's 1. So in this case, we call this a 1 by 1 square, right? And by the way, if you want to know the area of a 1 by 1 square, it's 1. How many 1 by 1 squares can you fit inside of a 1 by 1 square? 1. It literally takes up itself, right? How many 1 by 1 squares can we fit in a 2 by 2 square, though? Well, if it's a 2 by 2, then that means you can always take 2 and you can divide it. I apologize if my straight lines aren't so terribly straight. You can divide a 2 by 2 square, in half in both dimensions. So, this length dimension, I divided the 2 into 2 equally spaced, 1 by 1 lengths, right? And that should make sense. 1 by 1, 1 plus 1 adds up to 2 here, right? And then I did the same thing here. Notice this is, I split it, right? Let me change color so you can see what I'm doing here. So if we talk about starting here and then we go to this point where I split them in 2, well, that length would be 1. And then if we go from, again, the middle point here down to the end of the square down this way, again, that'd be 1. So notice I made a bunch of 1, right, by 1 squares. This square right here, just like all the others around it, now is a 1 by 1 square. How many of them are inside the 2 by 2 square? Well, there's 1, 2, 3, 4. Okay, so I can say that this 2 by 2 square has an area of 4. So it turns out we don't have to actually do this every time we want to find the area of a square where we have to like draw the lines and split it up, because it turns out all you have to do to do essentially the same thing mathematically, all you have to do is take the length and multiply it by the width. And if you do that, right, you will get the area. And a square is a special case because the length and the width, by definition of it being a square, have to always have the same value. So we could simply just call this length times length equals area. Or another way, if you have length times length, so the same number twice, we can write as length raised to the second power equals area. And sometimes you might have heard when something's raised to the second power, they say, the number squared. Maybe now you're seeing where that comes from. When you take, it comes from a square. If you take some number and you multiply it by itself, that's like doing the same operation you do if you're finding the area of a square. So that, as it turns out, that's why we call that, L squared here. And you could say L to the second power, but you might hear many times, mostly referred to as L squared. Okay, so hopefully, I've exhausted the reasoning needed to convince you of how to find the area of a square. So now let's talk about the square root, because that's what I really wanted to talk about. Now that we hopefully have a solid grasp on area, I want to talk about the square root. And so what I am going to show you is something you may or may not have already seen here, but if I get the right color here, so you may or may not have seen some symbol like this before, with usually some number underneath this little, overhang. And it turns out when you see it written this way, with a number underneath, not a hashtag, but some number underneath, we say that this is asking you to take the square root of the number, so the number you see underneath here. And what does that mean? What does the square root mean? Well, let's look real quick and say, what if we had the square root of 4? Well, this symbol, by the way, and this not the 4, but just this symbol is called a radical. A radical. And when you see it written this way, it's asking you to do something. It's saying, hey, see the number underneath here? That is an area of a square. And I want you to tell me what number or what root, meaning the side length of that square, did you need to have to give you that area? So what this means is the number you need for the length of your square to get an area of 4, we already calculated that. It's 2. If you have a 2 by 2 square, you'll have an area of 4. Okay, so that's the area. The square root's asking you to sort of go, it's asking you to essentially go in the reverse direction. Instead of using the length to find the area, it's giving you the area, and it's asking you to go backwards and figure out what the length was. And so it turns out that the square root of 4 is 2, because you need a length of 2, right, of a square, 2 by 2, to give you 4. Okay, so hopefully that's starting to kind of make sense, but I need to talk about more things, because this is a square root written like that, but that is not the only type of root. And so that's why I want to stress here, I didn't call this the square root sign, did I? I said it's called a radical. Why did I not call it a square root sign? It's because square roots aren't the only types of roots. There are other roots. There are third, or another way of saying that is cube roots. There are fourth roots, fifth roots. And we'll talk in a second about what that all means. So let's really quickly talk about a cube root. So I know this video is kind of covering a lot, so maybe I should have put it into 2 videos, but I figured out what the hell, just do one really long video. So imagine a cube for a second. I'm trying my best to draw a cube. Not an artist, so apologies if this looks absolutely terrible. And so, by the way, if you're not familiar with what a cube is, a cube has some pretty strict constraints the way a square does, where it has to, every angle inside has to be 90 degrees, and all the lengths, every length you see has to have the same value. So let's imagine a cube, right, that has, this dimension here is 2, and this dimension here is 2, and this dimension here is 2. Another way we can look at it is say the length, right, or if you want, I don't know, I think maybe we'll call that the width, why not? The width, not that it really matters, but let's say that's the width, and this 2 right here is associated with the length, right, and this one here is associated with the height. And so we're saying we have a cube here with width of 2, length of 2, height of 2. And if they weren't all 2's, we wouldn't have a cube, we'd have something else. And notice I didn't talk about this dimension here. Why? Well, because it's the same as this 2 here. It's a height. So we only need to talk about it on one side. We don't, because if this is a cube and this has a height of 2, then we know that this must also have a height of 2. We know that this backside, which is also a width, if this one's 2 and this whole thing's a cube, then this must also be 2, right? Everything is a 2 here. And so we talked about area of a square. And we said the area of a square is the amount of stuff or space, I guess, that fits inside the boundaries. Well, we can also talk about the amount of space that fits inside the boundaries of a 3-dimensional object like a cube. We're saying, like, how much stuff can fit inside this cube. And it turns out that the way we figure that out, again, we could exactly do what I said with the square. We could measure it in the amount of rice you can fit in there, the amount of jelly beans. But how about let's do something a little more mathematically like rigorous and defined, right? Because jelly beans have a like a varying like volume themselves, right? And so does rice, like individually, like they could slightly vary. Let's do something that we know is exactly the same everywhere, so it has the same exact dimensions everywhere. Well, we take one face and we divide it up into, squares, right? If this is 2, I can divide it up, to where I have 2 here, so each one is 1, right? And then I could take the top face and divide that up the same way, and this side face here. And I'm not going to draw because it's going to get messy, but I can do that with the back face, the bottom face, and this left face here. And then the idea is, if all of these cubes, now that I split it up, they should all, the smaller cubes that I've made, so let me show you what I'm talking about when I say smaller cubes. Imagine this top right corner here. I've broken it up, or I've divided it up like this, so that I have this little cube here that is measured, has a measurement of 1. I'm just drawing the back of it there so you can kind of see through it. Has a measurement of 1 by 1 by 1. Every, so it's a smaller guy like this. If I had, taken this and moved it out here, it would be like kind of like this, and we would say, hey, this is a length 1, or I should say a height 1. This is a length of 1. This is a width of 1. Right? So 1 by 1 by 1 cube. And I would say, how many 1 by 1 by 1 cubes can fit inside of a 1 by 1 by 1 cube? 1. Right? Itself. So it turns out that the volume, we call it a volume, by the way. When it's a two-dimensional object, we say the space inside that fits it inside is called the area. When it's a three-dimensional object like a cube, we say it's the volume. And so if you do 1 by 1 by, what am I doing there? 1 by 1 by 1, well, think about this. 1 times 1 times 1 is 1, right? But what about a 2 by 2 by 2? What we're saying is, we could figure this out mathematically here. 2 by 2 by 2. Well, 2 by 2 is 4. Multiply by another 2, you get 8. So 2 by 2 by 2, or 2 times 2 times 2 is equal to 8. And so I'm telling you by this math right here that we've done that we better have 8 smaller 1 by 1 cubes that fit inside this larger one. And in fact, we do. Let's see. The top right one here, we'll count that. So there's 1. The bottom right, there's 2. The top left corner, there's 3. The bottom left corner is 4. And then we have, these ones on the back side sort of that we're not looking at. Imagine if, this thing had a center like this going up, and imagine I rotated this cube about that axis 180 degrees, then this side, this back side, would kind of come around to the front and be in the same position that these are now. And if I did that and I counted it, it'd be another, I already counted 4, and then I would count another, 1, 2, 3, 4, and essentially we would have 8. And so it turns out that there are 8 1 by 1 by 1 smaller cubes in a 2 by 2 by 2 bigger cube. And so that's called the volume. Now let's go back and talk about roots for a second. So I showed you square roots, but what if I had something called a cube root, or another way of saying it's a third root? And so it has a number underneath, so let's write a number 8 for now. And the way you know it's a cube root is it'll have a little 3 here in this little nook. Notice the square roots don't have any number there. When you don't see any number there, that means it's a square root. It means you're finding some number that you multiply it by itself twice to get the number, the area you see underneath there, right? But when you have a cube root, you're saying, give me the number that you have to multiply it, 3 times to get what's this number here. This 8 is a volume of a cube. And so it turns out that the cube or third root of 8 is 2, right? Because, well, look right here. 2 times 2 times 2 is 8. Therefore, if your volume is 8, going in reverse, thinking about this in reverse, then that means the cube had to have side lengths of 2 to get there. And so The root itself is referring to the length of the sides of the cube or the square, depending on if you're talking about cube roots or square roots. And one thing I want to touch on is we are not limited to only square roots, right? Square roots and cube root. I'm going to put a little number in there because when there's no number in there, that's not a square root. It's just the sign, right? The symbol is a radical. But if there's a number, the whole thing is saying take the square root of that number, right? If I have the cube root of a number, right, you can have that. But guess what? We can have fourth roots of a number and fifth roots of a number. And guess what? It can go on forever and ever. And you could literally have the 1 trillionth root of a number, which would be hard to calculate. But it's possible. There's no limitation on this. So what does that mean, though? I gave you like real like geometric representations when I talked about square roots and cube roots. What about fourth roots, fifth roots, sixth roots? Well, it turns out I can't give you geometric representations of that because we live in a three-dimensional world. Notice I gave you a demonstration of a square root with a square. It's in 2 dimensions. We can see and visualize and think of 2 dimensions. We can even visualize, think, and see in 3 dimensions because that's the world we live in, a 3-dimensional world. 4 dimensions is interesting. Humans can think about it. They know it exists, but can we visualize it? Turns out we can't. We don't know where necessarily the 4th dimension is, or if there is. I think there's some debate on whether or not there is in fact a 4th dimension. I think a lot of science says that there is, but it's sort of locked for humans. We can't see it. We can't visualize it. So unfortunately, I can't write anything to show you what that means, but I can say that the way you figure that out is the same exact way. So if you had a 4th root, you figure out the same exact way you'd figure out a cube root. It's just, let's say we had the 4th root. So I'm going to write a little 4 there. The 4th root of 16. What this is asking is this number under here, I want to know, or not me, but this this operator rather, wants to know what number, question mark, what number multiplied by itself. So yeah, that number multiplied by itself 4 times to get this number, 16. So that's what you want to figure out. And if you practice for a little bit and you think about it, you'll find out that the answer to that is actually, so that the 4th root of 16 happens to be 2. And if you don't believe me, we can do it right now. If we do 2 times 2 times 2 times 2, we get 16. How? Well, let's look at this real quick. 2 times 2 is 4. 4 times 2 is 8, and 8 times 2 is 16. So 2 times 2 times 2 is 16. That means the 4th root, going backwards, the 4th root of 16 is 2. And so that's how you figure out, roots and stuff like that. So I hope now you at least understand the geometric representation of square roots and cube roots. And so in the next video, I want to actually show you how to solve more problems with roots, not just square roots, but all types of roots.